Hello, everybody. Welcome to the live stream today. My name is Ryan Sigler, and I'm joined here by Michael Ryaboy, and we are a data scientist and a developer advocate here at KX. And today we're really excited. We're going to be talking about a topic on chunking, specifically a more advanced chunking topic called semantic chunking. So with that, let's go ahead and get started. And one of the things I want to do while people take a little bit of time to join the session is just do a quick overview of our product and our vector database, kdb.ai. So kdb.ai, it's a vector database, and it's got a couple of interesting specialties. So it obviously has a great method for doing similarity searches upon vector embeddings. It has a hybrid search methodology, is really effective in fast metadata filtering, and as well as some specialized functionality for working with time series and temporal data. So that's one of our differentiators is working with time series data, and we have something called temporal similarity search, which allows us to effectively work with time series data, looking for trends, looking for anomalies, and other things like that. So with that, one of the great things about kdb.ai is that you can get started for free. And we offer a really packed free offering that has a lot of memory, a lot of storage, and unlimited read and writes right off the bat for you. So it's a great way to get started. And if you're interested in trying the vector database out, all you have to do is go up to the upper right corner on kdb.ai, click sign up, and you will get started. And once you do that, you just go ahead, put your email in, and you can also sign in using Google now. So you can use your Google account to create an account. And once you do that, you'll get an email just to confirm your identity, and you'll be able to create your own password. And then you'll be prompted to complete your profile. So here you just put in your information, your name, your company, and then some different entries to help us understand what are the use cases that you're interested in, and help us to tailor the product towards you. So for example, like, are you interested in document search, retrieval augmented generation, chatbot, things like that. So you can just fill in that information. And then once you do that, you've got access to our user interface. So here, there's some cool functionality in here. You can see sort of where you're at with your memory and your capacity. But once you get in and you can get your API key and your endpoint, then you can start actually using kdb.ai in your programs. So if you're interested in trying that out, we actually have some pre-built applications for you to get started really easily. So say you're interested in learning more about how to build a RAG pipeline with LangChain. Well, you could sign up with the process we just went through, come to the sample applications, and spin up RAG with LangChain sample. And you could do this probably within like 5 minutes from start to finish. So it's like a really quick and easy way to get started. And the nice thing about all these samples is that you can easily take them, work through them yourself, and then you could adjust them to your use case and use your own data with them. So really fast, easy way to get started. Highly encourage you to check it out. A little bit more about kdb.ai. On DB engines, we're ranked as the #1 vector database compared to a lot of the other competitors out here. So definitely reputable. And with that, I would just like to jump into our feature session, which will be on semantic chunking. So I'll pull up that presentation right now, and we'll go ahead and get started. So one thing I just want to mention is that if you're interested in asking any questions, feel free to go ahead and put a comment in. We'll be able to see this, and we'll do our best to answer live during the session. And if we cannot, then we will answer after the session or in the comments. So definitely ask away. All right, so semantic chunking. We're gonna do a quick agenda here. Quick overview on the vector databases and how that sort of fits into chunking. It really goes hand in hand. Why do we want to chunk? Understanding how to pick the correct chunk size, understanding some of the more traditional chunking methods that still work really well in a lot of circumstances. And then we'll go into semantic chunking. We'll understand what are the differences between semantic chunking and some of the other chunking methods, and what are the big advantages that it provides. And after we talk about semantic chunking, we'll actually do a code demo and jump into this, how you can implement this in practice. All right. So if you wanted to follow along or try out some of these examples, this notebook is going to be available after the session, and there's a ton of other samples up on our GitHub that you can open in Colab and try all this out really quickly and easily. We recommend trying it out with kdb.ai Cloud. What we just talked about getting signed up, that's how you get signed up for kdb.ai Cloud. And this is, I would say, the best way just to get started. So definitely check it out, kdb.ai. All right, understanding the vector database. So what I like to do with these presentations is sort of get a base level of, what is a vector database, how it works. And then when we get into the more complex stuff like the chunking strategies, this will make a lot of sense. And really the reason is because a vector database takes in the chunks that we're going to be creating, or you could consider it just to be takes in data. And it stores that data in a way where when a user comes in and sends a query or a question or a prompt to the vector database, the vector database is able to do a similarity search on all the data that it holds and return the most relevant data to the user. And once we do that similarity search and we return that relevant data or retrieve that data, then we can pass that off to our downstream applications. So one of the big popular ones right now, of course, is retrieval augmented generation, where we take that data and then pass it to a large language model. So that's sort of like the core purpose of a vector database. And if we look at like the take a step back and look at the overall architecture of how this works, is you have your source data. So this could be really whatever type of data that you're interested in. It could be documentation, images, video, audio, and you can take this and you pass it through an embedding model. And all an embedding model does is take that raw data and then it transforms it into a vector embedding. And a vector embedding is just a numerical representation of your original source data. So what's unique and powerful about vector embeddings is that they represent the underlying semantic meaning of this original source data. So it's not just looking at like, oh, what are the keywords in this document? No, it's actually telling you this is what this document is saying. So with that semantic meaning, when we store all these vector embeddings in our vector database and we query the vector database, we're going to get semantically relevant results back. So it's a really powerful method and functionality, and that's the core of what a vector database does. Okay, so when we think about chunking, it goes hand in hand with retrieval augmented generation. So what I want to do first is just a very quick overview of what is retrieval augmented generation, or RAG, and then talk about chunking and how that fits into this pipeline. So we have our data, and our goal with RAG is just to connect our data to a large language model. And to do that, we can implement this RAG pipeline. So what happens is our data is ingested and chunked up, which we'll be diving into here shortly. Once these chunks are created, they're embedded and then stored in our vector database, which is what we just went over. When a user prompts, that prompt is embedded the same way that all these chunks are embedded. And then we do a similarity search between the query embedding and all the embeddings that are stored in the vector store. So this is the first phase of RAG. It's often called retrieval. We're going to retrieve the most relevant and contextual chunks of data based on our user's query. And that means that a large language model will now be able to answer questions about the original data and send that response to the user. So that's the second step in RAG, called generation. So how does chunking fit into this? And chunking is sort of this first step in the entire RAG pipeline. So it's really important because this is what this is the data that's going to be passed through and stored in our vector database and then sent to the large language model. So it's a really important step. And initially, one of the big reasons people chunked was because we needed smaller pieces of data to send to our large language model, because large language models had more limited context windows. But recently, large language models have advanced and context windows have expanded. And I think this is becoming maybe less and less of a problem. But there still is a problem with this idea of just sending a ton of documentation into our large language model. The accuracy is going to drop because there's so much information. If we were to send, 10, 20, 100 documents to it at once, there's so much information in there, the LLM is not going to be able to sort that out as effectively as if we chunked and only sent highly relevant chunks to the large language model rather than a ton of documentation. So the point really is to split our documents up into smaller chunks, holding more granular information. That way, when we pass those chunks to the large language model, it has highly specific information to pull from. And that means it's going to have further reduced hallucinations and increase accuracy in responses for our user. So that's really why we want to do chunking. So now Michael is going to go ahead and talk a little bit about when we chunk, how do we pick the correct chunk size? So Michael, if you want to take it away here, that'd be awesome. And you're on mute, by the way.
I'm on mute. That's correct. Thanks for catching that, Ryan. Hey, everyone. So when you're doing chunking, there's a few considerations that are extremely important. And the most important one is the size of your chunk. Now, you have a few choices for chunk sizes. You could use a small chunk, and small chunks have the advantage in that they're likely going to be very similar in structure to your query. When a user is making a query in some kind of way, it's likely going to be a short one-sentence query. And that means that structurally, this chunk that's small, like one sentence long, is going to be extremely similar to that. But the disadvantage is that when your chunking is that granular, you're losing information, because what chunking does is it takes a piece of information and separates it from the context. And the greater the context, the more information that you have. So a large chunk size has the advantage that it actually has more context, which means less information is lost. It's less granular, which means it's going to be less similar to the query. But at the same time, it's going to provide better information. And when you're providing information to a large language model, it's usually better to provide large chunks, because small chunks often just don't have enough context to be able to provide the necessary information for a good answer. But here we're in a little bit of a dilemma. So small chunk sizes seem to do a little better for similarity search, but large chunk sizes have the advantage of not only are they better for large language models, but they are also easier for us to understand as people, right? As humans, like, we can read a large chunk size and kind of understand what is going on. It can't be too large, because at that point we're just looking at full pages and we haven't figured out what exactly we're looking at. But a little bit larger chunk sizes do perform better for retrieval augmented generation. So here we could do something that's a little bit of both. There's a strategy called chunk decoupling, or small to big retrieval, where we originally search based on single sentences or really small chunks. And these small chunks have some metadata, which is the larger chunk that they're a part of. And this means that we could search small chunks, but return to our LLM or user larger chunk sizes. And this way we can get the best of both worlds. Now, it's still going to have some challenges. For example, when you're searching small chunk sizes, sometimes that is missing information. But if your chunk size is too large when you're searching, it may have too many ideas enclosed in one chunk. And that's going to make it difficult to compare in multidimensional embedding space. So when we're doing chunking, there's a few different strategies that we could use. The first is and the most naive strategy is just naive fixed size chunking. And what this means is there are chunks completely based on the number of characters. We say, hey, we have a chunk size of around 100 characters, and we want an overlap. And overlaps are good, because with an overlap, we can encode more information per chunk, and we're not missing information that might be in the end of one chunk and the start of the other. So we have an overlap of, let's say, 10 characters, and we have a separate, which means like whenever we see two new lines together, we're always going to make a chunk breakpoint there. And there's a character text splitter in a library called LangChain that you could use for doing a lot of these operations. But this character text splitter is not very good in practice. What you find is that you end up making splits at arbitrary characters. You might make splits in the middle of a sentence, for example. You might make splits at the end of a sentence where it doesn't really make sense. You might make splits in a part of the document structure where you likely should not be making splits. So this naive strategy is the simplest thing that you could possibly do, but in practice, it's not very effective because your chunks are just going to be missing a lot of information and not split in a way that semantically makes any sense. There's a better option, and that's recursive character text splitting. And LangChain has this method where you once again set your chunk size and chunk overlap, but this is going to incorporate text structure as well. So it's not going to chunk at arbitrary locations based on characters. It's going to have a more robust strategy for chunking. It's going to first try to chunk by paragraph, and then it's going to chunk by sentence, and then it's going to start chunking by word and character in order to approximate your chunk size and chunk overlap. So it's still seeking to be around your chunk size. It's not going to be exact, but it's taking into account more semantic features in your text. Now, this strategy is still not extremely robust. Sometimes it makes mistakes. It's actually quite a challenge to effectively chunk text because the breakpoint of where one chunk starts and another one ends is always going to be a little bit arbitrary. And we could make these splitters more complex, and they're getting better constantly. But sometimes they do make arbitrary splits that probably shouldn't exist. Like a human can typically split much better than a lot of these libraries. And while this does look at sentences, paragraphs, and words, this doesn't take into account any semantic features. It doesn't actually look at the content of the text. Like, what is it actually saying? So this is a good start, and this works somewhat effectively in practice. And this is likely the most common way to chunk text that doesn't have a more robust format like HTML or Markdown. So if you have just plain text documents, this is a pretty effective strategy. So here, once again, we declare a chunk size and a chunk overlap. A small overlap is always useful. And then we just return just a set of chunks that we can then input into our vector database. There's another interesting strategy, and that's NLP-driven sentence splitting. So there are NLP frameworks like NLTK and Spacey, and they're integrated into LangChain. And you could use them to split text as well. And they look at some semantic features, so they could give you chunks that are very useful for some kinds of applications. For example, for NLTK, you can make chunks that have, for example, splitters based on numbers or figures or other semantic features like those, right? And even though this isn't used very commonly in practice, it is useful for applications where you do actually want to extract those pieces of information as separate chunks. So one way I have seen this used that was really interesting is someone used a splitter to split text, and they basically created cutoff points at each point and inserted numbers or tokens at each split, and then asked a large language model to chunk based on those splits. So a large language model can take the possibilities that the NLTK splitter created and chunk based on that for a little bit, just as an engineered solution to chunking. But again, in practice, this isn't used very commonly because the recursive character text splitter just performs better for plain text in practice. But this is an interesting strategy that should definitely be experimented with. And Finally, we have the Markdown header text splitter. Now, the Markdown header text splitter is a very effective strategy for Markdown. So the reason is Markdown has a lot of structure. And if you're just splitting by text or sentences, you're missing a lot of that structure that is inherent in a Markdown document. Markdown documents have headers, they have bullet points, they have all this structure that you could use to accurately chunk. And the Markdown header text splitter takes advantage of this structure for more effective chunking. So it's a chunking solution specifically based on Markdown documents. It also can extract additional metadata and add that to your chunks. It tags chunks with metadata that specifies which headers they belong to. So you have this advantage of not only being able to chunk more effectively based on Markdown structure, but you also have the additional metadata of like, where did this come from in Markdown that you could use in your application. You can also be more robust, and you could indicate exactly which headers to split on. Let's say you want to split it on header 2 because that's just how your specific document is structured. Well, you can do that as well. So it's robust and it's flexible, and for Markdown documents, it's likely the best solution you're going to get, at least for now.
Perfect. And yeah, one thing to add on this too is once you split based on the actual structure of your Markdown document, and there's another one, HTML document, they have a splitter for HTML as well. You could then apply one of the other splitters that we talked about, or the other chunkers that we talked about, to those subsections. So if you had a header that had a really large chunk of text within it, you could then apply like the recursive character text splitter to that. So you can kind of do it in a iterative way. All right. Well, thank you for the rundown on those chunking methods, Michael. Really appreciate that. And now we're going to talk about semantic chunking. And one thing I want to mention is that this is a more advanced method for chunking, but it doesn't necessarily mean that it's always going to be the best method. So it's something to experiment with. And I think it's a step toward, this sort of holy grail of smart chunking at some point. But I don't think it's there yet, though the results from this, I think in certain circumstances and use cases, could be highly relevant and really improve the performance of your RAG pipeline. So really excited to talk about this. And right off the top, I just want to say this was proposed by Greg Kemerat on his videos, 5 levels of text splitting for retrieval. So he has an awesome YouTube video. It dives into several of the more traditional chunking methods, and then he introduces this idea of semantic chunking. So all credit goes to him for that. So as we dive into this and sort of thinking back to some of what Michael talked about, this idea of setting like a global maximum chunk size or constant chunk size, it's really sort of a naive idea. And it's not something that in practice is likely going to give us the best results for creating effective chunks. And one of those reasons is because if you have these constant chunk sizes that you're working with, it's likely that you're going to end up having chunks that cover multiple topics within the same chunk. And really what we want is we want a chunk to only contain a very specific information regarding a very specific topic. And that means that when we embed that chunk, that embedding held within the vector embedding space will be focused specifically on a certain topic, which is exactly what we want. That's going to improve the retrieval of our RAG pipeline. So with semantic chunking, it's this method to optimize the chunk size of every single chunk. So that means each of these chunks will be more specific and more meaningful. And that's really the end goal. So if we look at this architecture of how this works, or this flow diagram, we start out with our document and we split up our document into sentences. So there's a couple ways you can do this. You could just split it up into single sentences. Greg, who proposed this idea, thought using 3-sentence initial chunks was a good method to go. But really, I think depending on the use case, you would just want to do some experimentation to understand, what should that initial split be. But for this example, we'll just say we split this off in the sentences, and then we just compare these sentences to each other using similarity search. So in a sense, we're doing what we did all the way at the beginning of the presentation when we're taking our data and we're embedding it and then doing a similarity search on it. You're doing that exact same thing, just with these small sentences. And we're saying, hey, is this sentence related to this sentence? Is sentence 1 related to sentence 2? And if it is related enough, then we can say, yeah, we can group these two chunks together because they're talking about the same topic and they're highly related. And then we could say, okay, well, is sentence 2 relevant to sentence 3? And we might say, yes, the embeddings are very similar, so we can group this as well. So we might then have a group chunk of these 3 first sentences. But then we come to sentence 4, and it's not really very similar to sentence 3. So in this case, we would then split that into a new chunk. And then we sort of just go throughout this process. So get to sentence 5, yep, it's related to sentence 4. So just looking at this example, we're grouping these sentences together by semantic meaning. And then once we have these groups chunked, we take these and then we embed them as a whole using our embedding model. And then we store this in the vector database. So what we're doing here is creating the most meaningful chunks that we can and ensuring that any pieces that we're tying together into group chunks are highly related. So this sort of optimizes the idea of having a small chunk where you have granular information and having a bigger chunk where you have more context. Or really, we're sort of bridging that gap here. We're specific on granular information within this chunk, but because we're able to group multiple sentences together, we're likely able to get more context that will eventually be passed to our large language model. All right, so how can we do this in practice? What tools are available to us? So number one, you could likely create this solution yourself if you have some coding experience. I think it wouldn't be too complex to try on your own. But of course, we have some easier options even than that with our favorite open source frameworks, Llama Index and LangChain. These are both frameworks that allow us to build applications with large language models and connect our data to large language models. So both of these have really good semantic chunking tools available to us. Some slight differences, but really at the core, they do pretty much the same thing, which is introduce highly meaningful chunks to our vector database. But for Llama Index, they have a module called Semantic Splitter Node Parser. And it has a couple things that you can do within this node parser. You can set your breakpoint. So that means where will I split into a new chunk at what point? How dissimilar does something have to be before I split it off into a new chunk, or whether I combine it into the previous chunk. And then you have the buffer size. So this is what we talked about earlier with how many sentences should be in these initial chunks. I think it defaults to 1. But you can try 2, you can try 3, and just sort of experiment to see what works best for your solution. And then LangChain has something called Semantic Chunker, sort of similar. It has a couple more breakpoint options, so you can sort of break this off by percentile, similar to Llama Index, or use standard deviation or interquartile. So you have some different options for determining at what point are we non-similar enough to split into a new chunk. So if we break this down a little further, go a little level deeper here on how this works, you have your document, you split it up into those sentences or small groups of sentences. All these sentences are embedded. And then because they're embedded, we can do that similarity search and understand, is sentence 1 semantically related to sentence 2? And if it is, then we can group them. But if we find that sentence 1 is not very related to sentence 2, then we would split sentence 2 off into a new chunk. And once we're complete and we have all of our grouped chunks created, we just embed that and send it to our vector database. So that's like the architecture of how this works, and you have multiple tools at your disposal for how to actually use this. And just in a moment, we're going to a code demo where we'll walk through how to do this in practice using Llama Index. Okay, one other thing I wanted to mention, and maybe one of the big benefits of using frameworks like Llama Index, is you get some sort of built-in tracking and citation tools within the chunks that are created. So once we create a chunk with Llama Index, which we'll just demonstrate in a moment, It has some different pieces of information. So obviously it'll have like the text that that chunk is. It'll have the embedding that is created, and it'll have some other interesting metadata. So it'll obviously needs to have a unique ID, which will show like this chunk compared to other chunks, so we can understand exactly where this chunk come from. But we can have some additional tracking to understand location within a document. So within a certain node or a certain chunk, we can look at the relationships around it. So we can find what was the previous chunk and what is the next chunk based on my current chunk. And then really good for citations, especially if you're working with a RAG system that was using multiple documents as source data, we can find the source document for each of these chunks. So if we want to go back and say, hey, where did we find this information? We can just look at the source document for that retrieve node. And once we find that, we understand, okay, this is where this information originated from. Also, you have the object type that's held within these nodes. So like document type, is it text? Is it a source document? Is it an image? Is it a table? You know, all this information is stored as metadata within these generated nodes. So with that, I'm going to go ahead and switch over to the coding demo. And again, if you have any questions about this, please go ahead and put them in the chat, and we will try to answer them live for you. But with that, let's go ahead and get into some code. All right, so we're going to do semantic chunking, and we're going to do it with Llama Index. So to do this, we have to install some dependencies. And I've already done this. We're going to save us some time here. So we install our pip install our Llama Index in our kdb.ai client. So this is all the tools that we need to build a RAG pipeline that uses semantic chunking. So once we have all this installed, we'll do our imports and import all the important modules that we need. And now we're set up to go. So at this point, we're going to go ahead and we're going to reach out and we're going to download some data. So at this, what we're doing is we're going out to kdb.ai. There's a ton of good Learning Hub articles there covering a variety of different generative AI topics. And we're going to download an article on time series insights using temporal similarity search. So if you're interested in checking that out, it's a really cool concept that uses time series data with vector databases. But we're just going to use this as an example document today. So if we want to take a look, this is what that document looks like. It's got some tables, it's got some text, and we're going to do semantic chunking on this. So first up, to do this, we need to do some API key stuff. So we're going to use OpenAI for our LLM and our embedding model. So I already put in my OpenAI API key. And then we need to set up some variables for Llama Index. So here we're going to define what embedding model are we going to use for this and what LLM are we going to use. So I'm going to use text embedding 3 small, one of OpenAI's more recent embedding models, and then GPT-4o, which is like their hot off the press LLM. And then we just pass this in as our LLM and embedding model to our settings for Llama Index. So at this point, Llama Index is now aware of the large language model and the embedding model that we are going to be using for this. So now we're going to do semantic chunking. And this is the fun part. So we're going to use semantic splitter node parser, which is their module for semantic chunking. We're going to use a buffer size, or the initial sentence split size, of 2. You can experiment with this. Try it with your own data. Try it with this. I believe it defaults to 1, and you could try it with 3. So really, it's something that you would want to experiment with. We pick our breakpoint percentile threshold, and this is how dissimilar does something need to be before we split it into a new chunk. This defaults to 95. I set it to 90. The lower you go, the more breakpoints and more splits there will be, so the more chunks that you'll get. And then we pass in the embedding model that we just defined above. So we're defining this semantic splitter node parser here. This is our semantic chunker. And now all we're going to do is go ahead and pass that document into that splitter. So now the document's going to be split into these nodes, and we can see it creates 10 nodes. So it took that document, and it did semantic chunking on it, and it ended up creating 10 nodes, or in other words, 10 chunks. So let's do a little exploration, and we can see, what does a chunk look like? And we see it. This chunk contains, a couple paragraphs. So we get to see here that like the chunks that are created with this, they can contain a good amount of contextual information, and it's just making sure that everything within this chunk is sort of covering the same topic. Now, we're going into that node tracking and getting a little bit of an understanding about how we could understand where are these nodes coming from and the citations. The metadata holds some of this information. So if we look at a node, say the first node that's created, node 0, we can see, okay, where did this actually come from? And what we see here is it comes from that document. So it shows us the source document, and it shows us that node type. It's coming from an object, or it's coming from the document object. So now we can understand, where did this node come from? And then we can see, okay, let's print out the previous and the next nodes. And well, because it's the first node, obviously there's not a previous node. But because we can print out the next node, then we could see this, print out the next node, and this would be, I guess, node index number 1. And we can see that this node object is a text type node. So this is just giving us a little bit more information about what these nodes are, where they came from, and what nodes are surrounding them. Okay, so you can see, there's all sorts of metadata that we can understand. You can print out all that relationship information here, showing the source node and the previous and next nodes. And then if we wanted just to print the entire node out, we can see all the information in one spot. So at this point, we have all our nodes. We're good to go. Let's create a RAG pipeline using these semantically split nodes and see how we do. So first up, we just set up our kdb.ai endpoint and API key. I've already done this, but when you sign up for kdb.ai, it's super simple to grab your API key and endpoint. You can just use this code right here and enter your API and endpoint, and you're going to be good to go. And then all we got to do is just connect to the session. So at this point, we are connected from this Colab notebook to kdb.ai, and we're going to be able to start doing creating tables and doing searches with it. So once we have that connection set, we need to set up a table schema. And this is just telling us, what are the columns that are going to be in our vector database. And we have a couple of columns here, document ID and text, where you're going to store the node's document ID and the actual text that that node holds. And that's going to be stored in metadata columns that we can then later see and work with. But really, the fun happens in this embedding column. And this is where we pass in the embedded text. So this is where the vector embedding is stored. We can define some attributes here. So what type of index do we want to use? You could use HNSW, you could use flat, you could use IVF. Multiple types of indexes available with kdb.ai. What search metric do you want to use? Cosine similarity, Euclidean distance, dot product. You can use any of those type of search metrics with our vector index. And then we just define how many dimensions are our vector embeddings. And this would come from the embedding model that you use. So whatever embedding model you choose, you just go and look up how many dimensions that is. In OpenAI's case, 1536 is the number. So we've defined our schema, and then we're going to go ahead and actually create the table. So what we're doing here is we're taking this schema and we're passing it into a create table command, which will just create the table based on that schema. So we're going to create a table called semantic chunking table and use that schema to create it. And at this point, we have a table that is created with this schema. And if we want to take a quick look, we can see here's the table. There's nothing in it. Those are the columns that we defined. So perfect. All right, so now we have our table created, and let's go ahead and insert our nodes into that vector database. So we just need to define kdb.ai as our vector store. It integrates perfectly with Llama Index. And then we use that as our vector store and insert these nodes into it. So this cell right here, this inserts our nodes into kdb.ai. So we can run this. And to check that our nodes are inserted, we will query the table, and yes, perfect. All of our nodes are correctly inserted into the vector database. All right, so now let's do retrieval augmented generation. And to do this, all we have to do is create a query engine, which is taking that index that we just created above, using that as a query engine and saying, hey, we're going to return the top 3 most similar nodes for our retrieval part. So we're going to get the top 3 most similar nodes from kdb.ai, and then we're going to pass that to the large language model, which we just defined. So at this point, we're all set to actually run retrieval augmented generation, and we're going to be using our semantic chunks to do this. So let's ask a question. There's a couple different types of similarity search that are relevant in the document that we just that we ingested. So we have transform similarity search, which is good for doing time series analysis on very large databases that hold a ton of historical data. And then we have non-transformed similarity search, which is great for like really fast flowing data where you want to do analytics on it immediately without having to build an index. We don't have to get too much into that, but basically when we print this response, this will go ahead and explain the differences. So it's able to actually go in, retrieve the correct nodes, and based on these semantically parsed nodes, answer this question, which is really quite complex, and you would only be able to find an answer like this within this documentation. So it's going to be able to get that correct node from the vector database and use it to send that to the large language model and generate this response for you. Now, one of the interesting things about Llama Index is you can actually go in and get information about the nodes that were retrieved. So if I wanted to see, okay, what were the 3 nodes that were retrieved? So to answer this question, what were the 3 nodes that were sent to the large language model? You can print these out right here. So we can see our node ID. What was the similarity score that we got out of the vector database? What was, in this case, we're using Euclidean distance. What was that similarity score? And then it's printing out what the text that was actually in the node. So all this, we can see each node. We can see the text that was within that node. And if we look through here, we'll be able to find where it pulled the answer from. And then maybe just one more example. And this is sort of an interesting one because if it works correctly, it will be reading information from a table within our document. So hopefully this will work. Okay, perfect. So it's actually pulling specific information out of a table. So 18.8 megabytes from a million vector index compared to 2.4 gigabytes for hierarchical navigable small worlds. So point is, what we're doing here is we're using these semantic chunks, and we're actually able to go in and read information off of a table from these semantic chunks. So let's see if we can find it in here. Right here, perfect. So it's actually getting that answer from one of the chunks that were retrieved. So as we can see, it effectively is using semantic chunking to answer these questions for us. And yeah, so I mean, that's really the presentation right there, and that's the code demo. If you're interested in learning more, or if you have any questions, feel free to check out kdb.ai and ask questions in the comments section, and we will answer those. If there's not any right now, which it doesn't look like, we will answer any more that come in after the session. Michael, did you have anything else you'd like to add?
No, that was really great.
Okay, well, perfect. All right, well, thank you everyone for joining. And one thing I want to mention is that I believe it's June 26th, we are going to be back and we're going to be doing a presentation on choosing the correct embedding model for your use case. So I think this is a pretty applicable problem that people have when they're working with understanding how to build a RAG pipeline effectively, especially trying to optimize it for production. Picking the correct the right embedding model is super important. So we're going to be presenting on that. And one of the other aspects of that is picking the right re-ranker to sort of tack on the end of your retrieval pipeline as well. So stay tuned. You'll be hearing more about that soon. That'll be announced. And again, thank you everyone for joining, and we'll see you next time.
Thanks so much for coming, guys.